So in this context, right, if we know our estimator, which is our probability we compute, right, the probability we compute again is a random variable. We computed the probability by averaging a number of indicator random variables, which is either true or false, either 0 or 1, right? So let's say look at the application. So our probability is computed by 1 over n. So remember, not 1 over square root of n. So we have to do a little bit of scaling. 1 over n of a summation of I goes from 1 to n of indicator random variables, right? So if I look at that number I compute, how do I use the central limit theorem? What can I say about how can I apply the central limit theorem and say some transformation of this probability is actually going to be a Gaussian random variable? Right, I just introduced you this theorem. Now it's time to apply it. See a little bit difference, right, in what they look like. Yes?
You say that each p is a random variable, and then you do that by.
So here, each I is a random variable, just like the xi above, right? Yes? Right, so the idea is perform a transformation, right? Some kind of a simplest transformation is linear. So, sorry. So maybe we can subtract this number with something and scale it with a number, right? So first of all, we can look at, does I have finite variance? Why? Yeah, because the value is only 1 or 0, and through a very simple mathematical derivation, you can see that for any indicator random variable, the variance of that is actually strictly bounded by a quarter, right? So any indicator random variable has a finite variance. So we can apply this, but how? We first need to correct for the factor, right? So why don't we multiply this p by a square root of n? Okay, so if we do that, we get actually the correct factor, right? So we have square over square root of n. Oh, I think I made a mistake over here. So so another condition is that they have to be IID with 0 mean. Otherwise the summation divided by square root of n, the mean is going to keep going up and up, right? So here all of this x has to be 0 mean. The converged Gaussian also has 0 mean. All right. Does it make sense? So what the central limit theorem says that basically says that if you take the summation of these ID random variables, the standard deviation basically goes like square root of n, right? Okay. So now I have scaled the probability we compute, which is this big P is actually not the real probability, it is an estimator of the probability. Itself is a random variable. The true probability is not random, right? It's a given number. But our estimator, the way we compute this P, the computed number is a random variable. Okay, so here we scaled this random variable to get something close to the form of a central limit theorem, but we still don't have the 0 mean property yet. So how do we get the 0 mean? Subtract by something. right? So what should I subtract so that the xi has 0 mean?
Or, sorry, root 2 over n.
Root 2 over n?
Yeah, root n over 2.
Root
So
n
the
over.
mean of the initial distribution is n over 2.
So let me ask you, what is the mean or expectation of xi of ii, sorry, of the indicator random variable? So here it should also be the, yeah, it's p, right? Because ii has a p probability of being 1 and the 1 minus p probability of being 0, right?
It's a different p than
It's a different p, so let me write as a small p, right? So this p is deterministic, is not a random variable. The big P is a random variable, so that's equal to p. And in order make the expectation of I to be 0, what should we subtract?
p over square root.
We should, for each, I mean, if we subtract each ii by p, right? Because expectation is a linear operator, it's actually equal to p minus expectation of p. I mean, because this p is deterministic, the expectation is equal to itself, so we get 0. So over here, so let's perform a further transformation. If I subtract p from every single one of these ii's, what did I do to this one?
Minus n times p.
Yeah, so if I subtract p to this one, at the end, what I effectively did is I subtracted the square root of n times p, right? So here, instead of square root of n times big P, I have square root of n times big P minus small p, right? And this can be applied to the central limit theorem. So which means the distribution or the PDF of this guy converges to a Gaussian of 0 mean as n goes to infinity. So as I take more and more samples, or if I take sufficiently many samples, the distribution of this guy is almost the same as a Gaussian distribution.